Hey guys, today we are going to talk about specific heat. And basically, this is looking at how heat is transferred between two objects. So when you touch a cold object, or when you have, a mug of something hot and it cools down in the room over time, any kind of heat transfer, not necessarily involving a chemical reaction, but just heat moving from one place to another. We already talked about the fact that heat naturally or spontaneously flows from hot or higher temperature objects to cooler ones. We're going to talk about measuring that and being a little bit more specific about that today. Okay, so um, specific heat involves determining the amount of heat transferred between objects. And I have just a sample question that you might be trying to answer with the concept of specific heat. It says how much heat is required to warm up 300 grams of water from room temperature, 25 degrees, to boiling. How would we figure that problem out? Okay, so you can see an equation there. It says Q equals C times M times delta T. Little triangle there means delta, which means change. And we'll talk about that more in just a second. Let's break these down one at a time and talk about what this equation means. Well, the whole point here is we want to know how much heat. And so it makes sense that our equation is already set up to solve for that. Because Q, which may not be readily apparent or obvious, but Q actually stands for the amount of heat transferred. So if you remember, we measure heat, of course, in what? Right? Heat is measured in joules, can also be measured in calories, um, but joules are what we primarily use. Okay, so Q stands for the heat transferred, and it's measured in joules. Okay. So how much heat is being transferred to warm up a 300-gram cup of coffee, maybe in the microwave or whatever, to get it up to the boiling point from 25 degrees Celsius. Okay, C, what does C stand for? This is our new concept. This C stands for specific heat. Now, specific heat is simply the resistance to temperature change. Okay, and so if you think about how long it takes to bring a pot of water, up to the boiling point, um, put it on the stove, crank up the heat, takes a long time, right? And that's because water has a really high specific heat, a really high resistance to temperature change. And there is a number associated with that. And if you look at this table, you don't have to copy this table down, but we'll use it from time to time. This table is a table of specific heats of different substances, and you might notice that liquid water here has the highest value on the whole table, 4.18. So that is because water is the most uh, resistant, at least among the substances in this table. Water is the most resistant to temperature change. You can add lots and lots of heat to water, and it doesn't change in temperature by very much. Um, One of the analogies that I always use is just from everyday life is if you think about a swimming pool, and the CK12 reading kind of talked about this a little bit, but if you if you have a relatively large swimming pool, say you go to a public pool, um, and an outdoor pool, and it's, let's say, the end of May, right when it's open, and sometimes at the end of May we have some pretty hot days already. So let's say it's jumped up to 90 degrees outside, but it's the first really warm day that we've had. Um, the pool water is still going to be super cold, even though the air has over, the course of the first few hours of the day has warmed up to 90 degrees. The pool water is going to be, if it's late May, it's probably going to be like 80, 82, whatever. It's going to feel chilly. The reason for that is because water has this high resistance to temperature change. It's about 4 times greater than air. So what that means is it's going to take that much longer for the water to warm up um, and, uh, and get up to the temperature of the air. And of course, the air temperature is not staying at 90 degrees. It's going to cool back down overnight and so forth. So it's going to probably take weeks for that pool water to get up to, maybe 85, 86 or something like that. Um, so that is specific heat. It's resistance to temperature change. Water has a very high resistance to change in temperature. It's also the reason that you have wild fluctuations in temperature in places that don't have a lot of water, like the desert. Um, if you've never been to the desert, if you go camping in the desert, it'll get down in the 40s at night, and then it'll shoot up to the 90s or even 100 degrees during the day in certain places in the desert, and that is because there is no water there. In places where there is a lot of water, like let's say the rainforest, the temperatures don't vary by very much because there's so much water there. And at nighttime, or excuse me, in the daytime, that water is slowly absorbing the heat from the sun, and then all night long, that water is slowly releasing that heat, keeping the temperature up. So you don't have those freezing temperatures that you might have in the desert, or at least really, really cold temperatures that you might have in the desert at nighttime. Now, if you're only experiencing going to the desert as going to like Las Vegas or Phoenix, then of course you're not going to experience that. It's still going to be really warm at nighttime. And the reason, of course, is because of all the concrete and buildings and stuff like that. That stuff will absorb a lot of heat during the day and re-emit it. Um, so anyway, let's get to the rest of the equation here. We've got an m and a delta T. The m stands for mass. As the reading mentioned, it does matter how big the pool is. If you're talking about heating up a pool with the sun's energy, a small pool like a wading pool is going to get warm in a couple of hours, whereas a big like Olympic-sized lap pool is going to take, weeks to warm up in the early summertime. So the mass matters. And then, of course, delta T, change in T means change in temperature. And it can actually be measured in either kelvins or degrees Celsius. It doesn't matter because even though uh, even though Kelvin and Celsius temperatures are not the same, so if you have like a 273 Kelvin temperature, that is equal to 0 degrees Celsius. But we're not really worried about the absolute temperature. In this equation, we're worried about the change in temperature. So if we go up by 5 kelvins, let's say, up to 278, that is the same thing as going up by 5 degrees Celsius because the increments on the two scales are the same. Okay, so we're only concerned with delta T, change in temperature. And for the example that I just gave you, the change in temperature would be 5, and that's all that matters, whether it's kelvins or degrees Celsius. Another thing I want to go back and say is, look at your unit for specific heat. It's really weird. It's joules over grams times degrees Celsius. Um, so I didn't say that earlier. It could also be joules over grams times kelvins. It really doesn't matter. And the reason it has that weird funky unit is because if you rearrange this equation to solve for C, well, you'll see that in just a minute, you'll end up with heat over mass times change in temperature, which has the units joules, grams, degrees Celsius. All right, so let's answer this question that we were supposed to answer here just a minute ago. How much heat is required to warm up 300 grams of water from 25 degrees to boiling, which is 100 degrees? Go ahead and say that right there. So what can we figure out from this problem? Well, we have 300 grams, and of course that would be our mass, right? That's our m. We have we're going from we're going from 25 up to boiling, so 25 up to 100. That sounds like a delta T of how much? From 25 up to 100, we would be going up by how much? 75 degrees, right? Okay. Um, and that's it, except we are also given the specific heat on this handy little table here. Because we know that it's water, And we can assume it's liquid water because it's at room temperature and it's going up to the boiling point. But so we're going to use water has a specific heat of 4.18. So we have this specific heat. So if I look at my equation, I'm solving for Q, heat gained or lost. Q equals C times M times delta T. Okay, so we don't have to rearrange the equation at all. We can just plug in the numbers that we just talked about. So we said that our C is 4.18 joules over grams times degrees Celsius. Our mass was 300 grams, and our change in temperature of the water was 75 degrees Celsius. So go ahead and plug that into your calculator, phone calculator, wherever you can access one, and let's see what we get. Okay, guys, and I got 94,050 joules. Okay, so, and if you notice what units cancel, and why I said joules was my unit for my answer, first of all, because we're looking for heat, and heat is measured in joules, but also because if I have grams on the bottom of my specific heat unit, and then on the top over here with mass, and then the same thing with degrees Celsius, that leaves me only with joules as a unit for my answer. All right, let's try another problem. Oh, and by the way, that's a big number, and that's okay because joules, we kind of talked about this before when we talked about the number of joules in a chicken sandwich or whatever. Joules are really, really, really small measures of heat. Okay. All right. How much heat is released by 2,500 grams sample of iron as it cools from 875 kelvins to 298 kelvins? Okay. So we are still trying to solve for heat, which means we still want Q. So we're able to use our original equation without rearranging it. So we're just going to say this. All right. So what I want you to do right now is see if we can pick out our mass in the I'm sorry. Let's start with the easiest thing. Mass in this problem would be that guy, right? What about our delta T? Yeah, the temperature is changing. It's cooling down this time. It's going from 875 kelvins down to 298 kelvins. And again, it doesn't matter that it's kelvins because changing by that many kelvins is the same thing as changing by that many degrees Celsius. So it doesn't matter. We're just going to go ahead and do the subtraction to figure out the delta T. And by the way, the change in temperature, whether it's going up or down, we just want the absolute value. So we're not going to have a negative change in temperature. We're just always going to do the bigger temperature minus the smaller temperature. So so that's my delta T, all right? That's right there. And then as far as the specific heat, we can get that from the table because we know that it's iron, and iron, of course, happens to be on the table. So let's go ahead and look at iron specific heat, and go ahead and highlight it. There it is. So iron has a much lower specific heat. You can see their metals typically have much smaller specific heats than like water does. So it's 0.449, okay? So we should be able to solve the problem. So I'm going to say Q equals, and our C is 0.449 joules over grams times degrees Celsius. Our mass is 2,500 grams. And our delta T, go ahead and do the subtraction real quick. What's our delta T going to be? Okay, so I got 577 kelvins. And actually over here, I'm going to change this to kelvins because again, it doesn't really matter degrees Celsius or kelvins, but for the purposes of canceling, I'm going to go ahead and make sure that our temperature units are the same. All right, so let's go ahead and figure out what we get here. Okay, so I got 647,683, and that would be, again, kelvins cancels, grams cancels, and that would be joules. Super huge number, but that's okay because joules are really small. And this was a large sample of iron, 2,500 grams. So a bigger sample is going to release more heat. Plus, it's going from super hot to not so hot. So big temperature change. Okay, one more problem. This time we're asking for the specific heat. So if I'm going to say what is the specific heat, let's start with our first equation, Q equals C times M times delta T, which one of those stands for specific heat? Right, so the specific heat is the Q. Sorry, the specific heat is the C. Um, so anyway, if we're trying to solve for C and it's being multiplied by mass and it's being multiplied by change in temperature, what are we going to have to do to get that C by itself? Okay, so hopefully you said that you are going to have to divide both sides by M times delta T, and that undoes what is being done to the C. In other words, C is being multiplied by M and delta T. We have to divide both sides by M and delta T. So there's our equation, and I'll rewrite it just to make it neater. C equals Q over M times delta T. And now we just have to fill in our numbers and solve. So we have our Q, which is always going to be measured in joules, so 1,612 joules. Okay. And then on the bottom we have our mass. In the problem we have a mass of 86 grams. And then we have our delta T, which is 25 degrees. It's being heated by 25 degrees Celsius. I want to caution you when you plug this in your calculator that we have to get our order of operations right. So we need to have like one big set of parentheses around the 86 times 25. Or you can just simply do that math first on your calculator before dividing. In other words, I'm going to go ahead and just rewrite this as 1,612 joules over, and then I'm going to multiply, get on my calculator here, and multiply 86 times 25, and I get 2,150. And since I multiply grams times degrees Celsius, those two units would get multiplied by each other on the bottom as well. So they're still there. I have joules on top, I have grams times degrees Celsius on the bottom. So now I'm just gonna divide 1,612 by 2,150. And I get 0.7497. I'm just going to call that 0.75, and then I'm going to keep my units that were all present here that did not cancel. And the last question is that a reasonable specific heat? 0.75. Looking at the table, yeah, I mean that falls. And again, this is only a small list of substances. But you can see graphite is around there, a little bit lower. So that doesn't mean that the substance is graphite, but at least it's a reasonable specific heat for us to get.